This is the Amp Hour Podcast, recorded September 30th, 2012. Episode 115, with guest Dr. Greg Sharbat, watcher of Wraithlike walls.
Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
And I'm Greg Sharbat from Butterfly Network Incorporated.
Hey, Greg. Thanks for joining us.
Oh, well, thanks for inviting me, Dave. It's great to be here.
And let's make fun of Chris. Because he's you said his tubes are still warming up in his lab there.
Yeah, and his router. He's he's waiting for the tubes to warm up. That's why he's not on the air yet.
He's been having serious issues. He's trying to dangle his mobile phone out the window, trying to get a cell connection, as it's called in the US, and then get a Wi-Fi repeater into his dungeon basement there. And we don't think it's working too well. So Chris may or may not appear for this episode. Feel free to jump in, Chris, if you're there. No. Fail. All right, Chris, you're from where? Tell us the story.
Okay, so let's see. Where am I from? Well, I just moved to Connecticut, okay? And
why Connecticut?
Well, I was working at MIT's Lincoln Laboratory for 4 years, and I was recruited aggressively to join a startup in Connecticut.
Aggressively?
Yeah. as a
Did
second
they send
founder.
guys around in trench coats?
No, they didn't. That was my last job. There were guys in trench coats, but
Right.
no, this one, we had people have been reaching out to me for various startup opportunities, as I'm sure they talk to you as well. And I can't reveal who our investor is, but he's a fairly famous guy, and he wanted to bring me in. And it turns out he and a student of mine started this company together, and the student was in my radar class at MIT. So they, from that class, they wanted to bring me in because I build stuff fast. So that's my
that's your
shtick.
speciality, huh?
Yes, I make things very fast, and so they want to build a series of prototypes to test a concept, which I can't talk about, unfortunately, because
That's
we're working
all right.
on IP stuff. But yeah.
I'm surprised that Valve haven't snapped you up, because you're aware that, I think 3 or 4 of our guests have ended up at Valve.
Really?
The software company, yeah. Yep.
Do they make hardware there?
They've got a hardware group. They've got a hardware startup group there, and they've sucked all of our guests.
What are they building these days? What are they making?
They're in, what are they building? They're gaming hardware. They're not allowed to say it's the next generation gaming hardware.
I see. They can't tell you anything, just like my thing.
Can't. That's right.
No one can say anything in this startup business.
All this IP crap. And
man.
Don't you hate it?
I don't know. We'll see. I might like it later.
So tell us about Lincoln Labs. We were talking about this before the show. How many people and what's the budget?
Oh, man. Lincoln Lab, first of all, it's an amazing place to work. They work on primarily government, military things, and FAA and NASA stuff, but mostly for the military, the U.S. military.
Mm-hmm.
And I think the budget is something on the order of not quite $1 billion, but close. Last I recall, before I left, and I think that they were well over 3,000 employees on their way to 4. And that was kind of where it was about a year ago when I joined the startup, and they're growing by by leaps and bounds, and they're doing a lot of important work over there. It's quite a place to be, actually. It was amazing.
Unbelievable. 3,000 employees. I don't think we have 3,000 employees working in the entire Australian electronics industry anymore.
You must have a few people, though. You make some pretty good stuff, though, these days.
Oh, well, we try and make some stuff, but geez, yeah, it's down in the noise. As far as those sort of numbers are concerned, it's ridiculous.
Well, we were just a lab of MIT,
I know. It's just
the biggest
one lab.
lab.
Crazy. So you've joined a startup now.
That's right. Yep.
Can you tell us anything about that at all?
Well, I can say that we're not a social network or Web 2.0 startup. So I figured that'd be a relief for you. we're actually making hardware, and we're working on next generation imaging and diagnostic equipment. And we have got a very small team at the moment, but we're trying to staff up. And so we're actually trying to hire digital engineers and FPGA embedded designers and stuff. So if you know any...
There you go. If any of our listeners are into that sort of stuff, go for it.
Yeah. And I wanted to say, if any of the listeners here are into that stuff, you can write me directly. But don't send me your resume. Send me pictures of boards you've designed.
Ah, there you go, folks. We've
That's
talked
more
about that one
impressive than
before.
CV.
That's,
yes.
No one cares about the CV.
No. Well, I mean, I think that HR folks might care about it, but all I care about are the boards and things you've created. I think that's the coolest part about engineering.
Absolutely. And you've created some very cool stuff, which we'll link into the show notes, no doubt. But you're into radar primarily. You're into tubes.
Oh yeah. Tubes are great.
Oh, okay, we'll have to talk
They're
about
so
that.
easy to design with.
Really?
They're so easy.
Okay, I've never designed with tubes. I guess I'm too young.
You don't know what you're missing.
Right. Oh boy. No, I'm not too much of an analog guy, let alone a tube guy. So there you go. Please extol the virtues of the tube.
Well, I have to say, I think it all started when I was a kid. My parents were very supportive, and they'd pick up these old television sets for me to take apart.
Excellent.
Back in the early 80s, everyone was throwing out their tube stuff by then. It was all dying off, and so I took apart a lot of tube stuff, and I think that it was just wired in early on that I had to do things with tubes. But the audio, so I got into making tube audio gear for fun, and got out of hand with it by making the vacuum tube home theater system that I have. That just was a little crazy.
I've seen it. It's a huge 40-foot rack, 4-foot high, 6-foot high rack or something.
That's right. Yep.
Crazy.
Yeah, it's full. 23 tubes and I can't remember, 16 or 20 amps of filament current, and the plate voltage is 535 volts DC. And look, right. I like to tell people it's about efficiency. Okay, so where else could you both get amazing and loud home theater sound, high quality sound, and heat your living room, all for 1 kilowatt.
All for measly 1 kilowatt.
For 1 kilowatt. It's a great deal.
Oh boy, because these are like 400 watt per channel amps, right?
Well, that's peak. So I
oh right, okay.
Someone asked a really good question on the comments, which was, "You're really getting 300 watts?" And I'm like, no. I think there are different ways of characterizing output power of audio amps in any amplifier. Yeah. So that was peak, and really RMS I think is there's a 4-channel amp. It's 80 watts per channel RMS, and then it's 55 on the single mono-channel amp. So
right,
that's RMS. Now, if all 4 are going at 80 watts, the power supply starts to sag.
Okay.
And then they'll start clipping probably around, after a while, probably 50 watts, 40 watts, and somewhere thereabouts.
You need a beefier power supply with big copper bus bars running throughout the thing.
Oh, no. You don't need that with 600 volts DC. You just need little wires.
Of course.
Yeah.
That's it. Hence the high voltage,
400 milliamps at most, That's it. But, the power supplies sag with tube stuff. It's weird because we're so used to, in the solid state world, digital world, you have regulated power supplies. They don't sag.
Yeah, that's right. Well, as long as you design them right. Well, they don't sag, they drop out, and then they can do all sorts of weird and wonderful things when they drop out. They can oscillate and do all sorts of stuff. But, these sag, and that adds to the warm ambience of the sound, does it?
I don't know. Sometimes that stuff can be bogus, but
right.
When it sags, it definitely it really you just lose peak power, and it'll start to distort when it sags. But I've thrown some parties in college with that system before, a number of parties, and we've had that thing going, early into the morning, very, very loud without any problems. So no sagging going on.
Speaking of college, you were saying before the show that how long did it take you to figure out how to get girls, how to meet girls in college?
Well, okay, so I love the hobby of amateur radio. I've been into it since 13, but when I went to college, I really wanted to meet some girls, and it took me 5 years of college to realize that the girls generally speaking, not all the time, but they're not. Most of the time, the girls are not in the amateur radio club. You got to go. I realize somewhere you have to go where the girls are.
Oh boy! And it took you almost your entire PhD to figure that out.
Yeah, it did. And finally I decided to learn how to swing dance, and then was able to meet. Now I'm married. We met at a swing dance, my wife and I. So.
There you go. Very good.
Yeah. So it worked out well. So now I can just go back to ham radios.
Right. Now,
Hopefully she's not listening.
Yeah. Of course she's not.
No, she won't.
No, wives don't. No, they don't pay. They don't pay any attention to her hobbies, do they?
No, basically
they
not.
just couldn't care less.
And sometimes they even.
Hey.
Yeah, I made it. I snuck in here. Sometimes the only thing they do is they loan us their phones so that we can hook in with 4G connections with their
that's
cell
being
phones.
very supportive.
Oh yeah, it was.
Yeah.
You aren't going to wind up with a bill of hundreds of dollars, are you?
Oh, I'm watching it like a hawk. We'll see. We'll
right,
see, guys. So I take it we are live right now, or live.
We are live. Yeah. Yes, we're 15 minutes into it. Yeah.
Oh man,
you're way out, dude. Now, what's this
sure
0.46% distortion that you proudly quote on your website for your Valve amp? What is this? I thought, the whole idea of having a tube amp is so that you get that warm, fuzzy Valve sound, and, you want distortion.
Oh, no, I want to make... It is. And, honestly, I built them just to learn how to work with tubes and just build a high-performance amplifier. I wanted the lowest distortion possible. I designed the feedback control system, undergrad control system theory, and applied it to the amplifier and calmed its oscillations and, got
and
less than 0.5%
distortion.
That was not trivial.
Right.
I'll tell you what, most of your time when you design a tube power amp, a good one, is going to be spent actually compensating the network, or making a compensation network to keep it from oscillating.
Yeah.
The fun Valve, soldering the resistors together, point-to-point wiring, that's nothing. That's a week.
Uh-huh.
Measuring every single frequency plot manually with an old Tektronix oscilloscope and an analog signal generator, you kill a lot of weekends doing that.
Now, here's an interesting fact which is thoroughly fascinating. If you go on to Greg's, look at all the stuff we'll link in the show notes of all the stuff he's designed and done. You've actually never laid out a PCB.
Never. Not once.
Wow. Now, insert PhD jokes here, folks.
I don't know the faintest idea how to do it. That's why we need those board designers to join my startup.
I was going to say, didn't you say that's going to be the interview criteria, is if they have laid out a board? Because
yes, that's a prerequisite.
That sounds a little hypocritical.
So Stardust just filled with PhDs who can't actually hold a soldering iron or lay out a board. Well, you can hold a soldering iron clearly, but. Yeah, sorry. We just love making PhD jokes here on the Amp Hour. It's a staple.
Oh, you'd be surprised what you could do without laying out boards. You can do a lot.
Oh, yeah, of course. Point to point. Tag strip?
Yeah.
Yeah?
Yeah, tag strips. Those terminal strips with the lugs on them, and then you got the proto boards, and then the wire wrap. Now, that's the best.
Oh yeah. Boy. Now we're talking.
We have some pictures on previous episodes of there's some pretty epic wire wraps on Flickr if people search for that stuff. It's just they're doing like digital, 64 lines at a time stuff. It's just insanity.
Now, are these new boards they're making, like the prototypes, or they're just from old vintage?
Oh no, these are very legacy. Yeah.
Wow.
But that goes to show how diverse the electronics industry is. You can be a top-notch industry designer, yet never have laid out a board. Never have held a soldering iron, for example. Some of them never do it. They just all they do is design chips, or And I know people, top-notch board layout people, never soldered in their life.
Wow. Really?
And it is so diverse.
It depends what your thing is too. Like,
I think a lot of companies want that, right? I mean, they want or even institutions like schools, they, especially PhDs, I'm sure you could speak to that, Greg, they want very focused work. And so if you don't branch out yourself like you do with, hobby stuff, then how do people get it?
Yeah, I would say that had it not been for hobbies, I just,
you wouldn't have designed any electronics,
yeah.
right? Yeah.
Yeah, hobbies are key. You need to have the hobbyist interest.
Some people don't, though. Some people have a job where they don't want to do any electronics on the outside because they get their full fulfillment at work. And, well, okay,
Man.
But I found that's rarely the case, though. So especially the stuff you're truly interested in. It's pretty rare that you get a job that has, smack on exactly what you want to do. So...
Well, at Lincoln Lab, I was doing a lot of managing of programs after a while, and so I would go home and fix a valve, an old tube radio, or improve the feedback control system on my stereo or something. Then get the engineering fix. You don't want to lose it. You could lose it easily.
Of course.
Careful.
Oh man. But one of your big things is radar, right? Tell us about that. How did you get into radar? Was that part of your PhD and your stuff?
No, actually, where I went to school at Michigan State, they're not really known for radar. But if they find a grad student who's ambitious enough to try to teach himself or herself, they'll give you enough rope to hang yourself. Basically,
okay.
Go ahead, go knock yourself out. So when I was 16, I was working on a radio telescope for the science fair, and it was really nice when it has all analog swept frequency. It could track signals and things. It was neat. It was very interesting. And
awesome.
I toured the Big Ear radio telescope at Ohio State University. This was 1996, and one of the volunteers there was an astrophysicist who co-founded this company that built radar systems, small imaging radar systems to image stealth airplanes, basically.
Right.
And it's called Lintac was the company, and they were bought out by Aeroflex at some point shortly thereafter. And so I was asking all these technical questions to the people at the radio observatory. Hey, how'd you do this? How'd you do that? Because I'm trying to make one,
Yeah.
Well, how do you deal with this problem, that, and the other thing? And then so he goes, hey, yeah, those are pretty good questions. You want to intern? I was only in high school at the time.
Awesome.
So I'm like, sure, yeah. So they brought me down to this company and showed, I was working with these radar systems. I was doing a lot of wiring, cables, connectors, boards, and then they showed me how to use the 8510 network analyzer. So I'd sweep amplifiers, this, that, and the other thing.
Nice.
Then I would help repair radar ranges. Like they had there's one range in Dayton. I had to go up there and repair the actuator, the azimuth actuator, and so anyway, that's what got me into radar because you could actually make imagery with microwaves. I thought that was fascinating.
It is, and you're now teaching a course, are you, at MIT about
that's right,
actually designing your radar thing using tin cans? Tell us about that. How did that come about, and how does it work?
Well, I was at Lincoln Lab. Lincoln Lab's a really cool place, and they had there was this guy, this division leader. His name is Bob Shin. He's a really interesting guy, and he sent out this note saying, "Hey, we need to." What division head is a very high level at the lab. You're it's a pretty flat organization, but that's one of the people at the very, very top.
Right.
And so he wanted to put together a class for it's called IAP, Independent Activities Period class. At MIT, they use the month of January to just be a sort of a free-for-all where the students can take whatever courses they want for fun.
Oh, okay. Fantastic.
Yeah, and really almost anyone can teach a course there.
Right. You don't have to be you don't have to be a tenured professor or anything.
Anyone can. And so
right. Interesting.
The laboratory,
we get Dave as a guest lecturer.
I could be a guest lecturer at MIT. There you
Seriously,
go. That'll look good on the resume.
I'm sure they would take you in a second if you wrote up like a week-long class or something. You could teach it. Yeah,
Shame it's
apply
12,
online.
14,000 miles away.
Oh, yeah. Maybe you could do it by teleconference.
Right, teleconference. Yeah, Dave appears on a big screen.
Yes, a huge one, And they have a little camera there looking at everybody else.
Oh, cool.
Yeah, so, this is how the lab thought that the lab was trying to, improve their relationship with campus because the lab is in Lexington, Massachusetts, and campus, of course, is in Cambridge. Mm-hmm. And the lab's doing the, government, military stuff, and campus is doing all kinds of stuff. So, they're always trying to sort of improve the relationship. And so they thought, well, this is pretty low-hanging fruit. We can offer a class on radar.
Terrific.
So they came to me, and I wrote up a little short proposal, and I said, hey, when I was for my master's thesis, I built a imaging radar system, from scratch. I've built lots of radar systems in grad school, but my first imaging radar system was made out of some waveguides and stuff and that, horns and things. But the cool thing about it was I made synthetic aperture radar microwave images with it by laying out a piece of measuring tape and translating the radar manually every 1 inch, and then hitting enter on a lab view, VI, and then it would pulse the radar when I hit enter. And I did that 138 times, and it would make imagery, though. It worked.
Sweet.
Wow.
So I said, hey, you know what? What if we do this with parts that are at lower frequency, where the parts are a little more available? And, what if we did that and we had everyone make a synthetic aperture radar system, a microwave imaging system? And
Why
I
not?
said, why not? Look, it's been done
Yep.
before, and they jumped on it.
So do you now do the same thing with the enter, or do you actually script it now so that it actually?
No, it's worse than that even.
Oh.
But
You have to hit a button or something.
No.
You get an enter key, you get a push button or a dip
Well,
switch.
here's the thing. If you're going to build this radar, it's got to be cheap because you're trying to give it away to the students. So it's got to be very, very cheap. So this thing was built we use coffee cans for the transmit and receive horns. That's why there's 2 of them. We used some mini circuit stuff, and we bolted all to a block of wood, like an old 1920s radio.
Yep.
So it gave us cheap and also gave us something that was very transparent. You could look at it and see how it works, understand it conceptually. So how we acquired data was we used the audio input to your laptop as the digitizer for the radar. And so what you would do is the right channel would be what we call the video signal or the baseband signal, and the left channel was a synchronization pulse.
Got it.
On the rising edge, you knew the radar chirped.
Yep.
And then I wrote a little MATLAB script that would look for the rising edges and pull the data off, the D-chirp data off the right, and then bin it into a little array. And so that's how the radar worked. And so when you would form a synthetic aperture image, each kit came with a 50-foot tape measure. You lay that sucker. Well, first step is find a straight and level surface.
Right.
Step 1. Step 2, put this 50-foot tape measure out there. And then step 3, you really got to want it. Okay.
Right. Okay.
You really got to want it.
Right. This isn't for weaklings, right?
No.
This is not a flashing lead class, folks.
No way. No. This is you got to want this image. Okay. Now, step 3, you line the radar up the left side of the block of wood with the first mark 2 inches. Okay. And there's a little toggle switch in the kit, and what the toggle switch does is it mutes the left channel where the sync pulses are flowing out of the radar. And so you mute the left channel, move it 2 inches, unmute the left channel for a good 1 Mississippi, 2 Mississippi, 3 Mississippi. Then you mute it.
High-tech engineering here, folks.
Yeah. You slide it over 2 inches and unmute it. And mute it, slide it over 2 inches, unmute it. And, of course, you count your 1, 2, 3 Mississippi. And all the while, you record a WAV file.
I feel like you should have a different count instead of Mississippi. It should be like 1 Feynman, 2
Feynman.
Feynman, something like that.
I guess we could have, but I don't know. I like it. Yeah, you're right. I like it. Keep things simple.
And this finally produces an image at the end after all this massive amount of processing.
Yeah, it does. It will create an image. It's a very coarse microwave image, but the idea is you want to differentiate targets in range and cross range. So, away from you and across the synthetic aperture that you just acquired. And we would instruct the students to find really big metal objects and image those.
Like,
Right.
for example?
The Alexander Calder, it's the Great Sail. There's this huge metal statue on MIT's campus called the Great Sail. And when you image that thing with a coffee can radar, it's this big metal thing. There's lots of multipath within the statue, just bang, bang, bang. And then you get this amazing image. It looks like a wood screw after you process it.
Terrific.
Yeah, it's really cool.
So how do you have to rotate I know absolutely jack about radar. Okay, so I'm a total noob here. Do you have to rotate
Yeah, I mean,
the thing? Like, do you have to go all 360 degrees around the object?
No.
How does it
Well,
all...
there are different ways you can do it, and the way we do it was we make a linear synthetic aperture. So we set the tape in a line, and usually we tell everyone to find like a rail or something, or put a couple of 2x4s out there on some sawhorses,
Yep.
and you just go in a line, and that's how this you can circle it. That's another way of doing it.
Okay,
but it's easier to know where you are on that with a couple of 2x4s and sawhorses.
got it.
So but this is, mind you, this is the last of 3 radar experiments you do. Mm-hmm. The other 2 are not as rigorous. The first is a Doppler experiment, and the second is just ranging. And the third finale of the class is always the SAR image.
Right. So you go in a straight line, pointing towards the center of the object. So you have to adjust as you move out from the line. Do you have to adjust the angle, or no?
You don't. You just it always points out.
So it's always pointing straight out, even though it's not in line with the object?
That's right, yeah.
Right. Okay, so how far can you go either side before, you're not seeing the object anymore?
Yeah, let's see. The beam width of the coffee can antennas is about 70 degrees.
Oh, okay, right.
They're floodlights, man.
Okay, got it.
You cannot miss
it. Right, got it. So you can keep going for a mile and
you
still
can
almost
go for a
hit.
mile and you'd still see it.
Right. Got it. And there's lots of advanced processing that eventually stitches the image together?
That's right, yeah.
Right. And that's all a MATLAB script?
Yep, and if you go to the Open Courseware site on MIT's MIT.ocw or something, we'll put in the...
So it's all there. So people at home, following along at home, can build their own coffee cup radar.
Everyone can build one.
Fantastic.
And so you said this is all kit form. Does that mean people can buy the kits too?
They can't. Like a thing? You have to. There's a bill of material, and you have to order everything. There's several hundred parts. It's pretty tedious, but
really?
It works.
Wow.
It does work, and that's the funny part. You just have to have a little bit of faith.
Got it.
Wow.
But I get emails about once a week from new people who've actually taken the plunge and built this thing, and they share their results and stuff. It's pretty sweet. A lot of people have built it. It's being adapted all over the country. Actually, UC Davis actually took this concept. This class is like a 1 to 3 week class in its current format. This guy at UC Davis turned into a 1 semester long course on radar.
You had mentioned in an email, too, about this experiential learning, and like you're really big into that stuff. I mean, like you said, UC Davis is doing that, but I mean, is this a wider trend you're seeing, or is it more limited still?
I think it's a wider trend. I find there's a huge demand for this sort of thing. Big time demand. It's pent-up demand, actually. When I architected this course, I set it up, I wrote the course to be how would have liked to learn about radar,
Yeah.
What would be the ideal course? And that's what I did. And the ideal
build
course
something
for me
that
would
works.
Build it. Yes.
Yeah, exactly. Who wants to go deep into radar theory? It's probably boring as batshit, right?
Oh man,
well,
yeah.
The question is why it took so long for it to get to that. I mean, like, why did it? Why isn't it always been like that? I guess is the question.
I have no idea.
I'm a huge fan of working backwards. You start with something. Well, here's, you build something or you have something that works. Here it is. Okay, now let's go to the theory and figure out, how that works, and not from the physics level, like, from the modular block diagram system, that top down kind of, not from the bottom up, let's learn quantum physics and bloody, electron physics and everything else, and then we'll work our way up. That's just bullshit. How can anyone keep interest like that? I don't understand it.
I don't know either. I mean, all I can tell you is
I was
that's
the
how
most
they teach
at university, right?
Well, yeah, I know.
Many of them.
I never really paid attention in college or school ever, really. I was drawing circuits on the margins of my textbooks the whole time. So I wrote it like that. Like I figured, what is the right way to teach this? And like just like you said, we would have high level lectures, sort of explain to you the basics. We would get into the physics. Right. And we'd say, all right, now we're going to build this and do this experiment and email us your results. So they'd email us results and we'd post them up on the the big board there and call on the teams who acquired this result, and we'd ask them to explain why does it look like this. And what had happened is sometimes people wouldn't know, understandably. So we would start diving into the more deep, in-depth radar theory that we understand at Lincoln Lab, and people appreciated it at that point. And
absolutely,
they're very engaged. I'll give you an example. Like, it's in such a demand that we had a MIT professional ed version of this course. So we took the IP one and we turned it from a 3-week course to a 5-day course for professionals. And in the first time we ran it, which was August 2011, we filled the course with 30 people plus a waiting list.
Wow.
That's the kind of demand for hands-on learning that's out there. And we were the first hands-on learning professional ed course at MIT that was open to professionals like yourselves or myself.
Yep.
Yeah, and we were the top-ranked professional ed course at MIT in 2011.
There you go.
Yeah, we did really
and
well.
There's that many people who want to, that many professionals who want to learn about radar, is there?
Oh, yeah. In matter of fact, it's been spun off to the MITRE Corporation. They now have their own version of it where they use the coffee can radar and our lectures. And like I say, UC Davis, and we actually ran there's an internal one at Lincoln Lab, and there's one for the Air Force that they do. There's, it's sort of going, which is awesome.
It's great.
Is there a simpler way to do it? Because you talk about, like, there's the bill of materials is a couple of hundred items, and there's, is there a simpler, cruder way to do this and get something running?
I would say, in terms
or is this the minimum investment you need before you can get a SAR image?
If you could print this design onto a board, it could become a lot cheaper. I think you can get it down to maybe the $200 price range.
Right.
Okay. With surface
I think that might be a call for our listeners. Maybe one of our ambitious listeners would like to do that.
Yeah,
kind of thing.
Go for it. I mean, there is a huge demand for the kit in a real kit form where you don't have to order the bill of material. And if we had it in a kit form, it would have even wider adaptation, I'm sure.
There you go. There's a project, and it's all open, right? So somebody can take all the circuits and everything and come up with a presumably still open source, because you can't just steal someone's stuff and close it. Right. So, no, they could come out with a kit,
sure,
I guess, and be the kit supplier.
That's right, and they could build it better and make improvements. There's a lot of room for improvements, I will be honest. And, I would love to see that, because it would greatly improve access to this sort of learning experience.
Now, you've been working on a radar which sees through walls.
That's right, yeah.
Tell us about it. How does it work?
Cool.
What type of walls? How far
concrete.
Can you just see a blobby image, or can you actually see people's faces?
Oh, of course, blobby image. Yeah, right. There's no way you're going to see faces or anything.
So what distinguishes a person from a big metal statue?
Movement.
Like you were going for.
Yeah. The statue doesn't breathe. Yeah. It's true. Statue doesn't breathe.
I've heard about that with statues.
So you can actually physically see someone tell someone's breathing even if they're not moving.
Yeah, you can if you want to. We've done this before. You can actually measure their breathing rate.
How does that work? Please explain.
That is creepy.
Yeah, it's.
Can you? Is it their chest expanding or what?
Yeah, that's all it is. It's just they're moving.
Right.
They're moving very slightly in the.
Right. So it's still based on movement.
Yeah.
Right.
So one of the videos that you had linked us to, though, it looked really blocky. Like, how can you even see that? It seemed like it was like 20 pixels kind of stuff. It didn't. Has it progressed since some of the prior press on this thing?
No, it's that's about it. And the thing is, let me think about the resolution. I think it's on the order of maybe. I think it's about 0.5 meter by 4 inches or something like that. It's kind of a rectangular block. That's the resolution, and it's limited to the physics of the aperture. The antenna array, which is the physical aperture, and the antenna array is 8.5 feet wide. So the center frequency is 3 gigahertz. So you can only do so well in resolution.
And if you go up in frequency, I'm assuming then you would have problems with absorption and penetration and all that. So you can't just arbitrarily go up in frequency and get better resolution, right?
You won't get through.
Yeah. You don't get through. So what is the range of frequencies that can get through? What, concrete, presumably?
Yeah, concrete. Oh, really, I think any microwave signal will get through. Concrete just depends how much.
Right.
How much gets through.
Yeah.
So we're at the upper
much gets
end.
Back.
Yeah, exactly. the frequency of operation for our system at 3 gigahertz was at the absolute highest frequency people attempt through wall imaging. Really, most people, it's UHF, 440 megahertz or maybe 1200 megahertz or somewhere thereabouts. It's almost never 3 gigahertz.
Got it.
And what we did, we chose that because we wanted resolution. So let's say we went down to 400 megahertz. Well, we'd have to have an aperture almost 10 times the size of our 8.5 foot aperture to get the same resolution. So that thing becomes ridiculous. Like there's no way you can bring that.
Antenna has to be bigger than the room room you're imaging.
Yeah, it'd be ridiculous.
Yeah, and I imagine this stuff like you're selling it to like the DoD or something like that. It's like, well, this thing can see through tons of concrete, but it's about 40 feet wide. So
you need a semi-truck.
They've got visions of all these soldiers coming up with their little with their little X-ray vision camera.
Yeah, that's not going to happen. No,
right.
They're not going to get that. Not with this technology. I mean, not with microwave imaging. No way.
So those X-ray specs they advertise in the back of the comic books, they're bogus, are they?
Oh, I cannot answer that. I don't know. I've never tried.
Well, that's good because our one of our listeners was very worried about people coming to get him. I don't know if he has particular issues, but he was worried about people seeing through walls.
Well, I wouldn't worry about this thing being adapted widely anytime soon. It's a prototype, and it's there's every time we would get it out of mothballs to use it, something else would break, and it costs a fortune and all that. So it's very much a laboratory thing still.
And you can't defy the laws of physics, Captain. It just requires big antennas to do this.
It does.
And even then it's crude. So, if somebody's parked a 40-foot shipping container out the front of your house, then maybe be concerned that there's, but
start to get nervous.
But apart from that, no, that black van out the front.
When the moving company is.
Yeah, that's
right.
Yeah.
It's like a moving van or a flower van, and all the guys are wearing sunglasses.
That's
it's like,
right.
Then you get nervous.
I don't think you have to worry. But they're the ones shooting lasers onto your window, so they can hear everything you're saying.
Right?
So,
they don't need our radar for this.
No, and they've got their Tempest, stuff, which allows them to pick up everything you're viewing on your monitor and all that sort of stuff. Be afraid. Be very afraid. I highly recommend the tinfoil hat. Works well.
Actually, if you wore the tinfoil hat...
Are you able to vouch for that?
With our radar, you'd show up more strongly with the tinfoil hat.
There you go.
Yes. So it would do the opposite.
Oh, that's such a great idea because the crazies out there. Oh my god!
So they're actually making themselves more visible.
Yes,
I
way
love it.
Easier to pick up with the tinfoil hat. And actually, we found
awesome.
If you carry anything that resembles a firearm, you become more easily detectable as well. By about 10 times as much signal will be reflected in that case.
There you go.
Yeah, because it's steel. Anything metals just really lights you up.
That is solid.
Yeah. But yeah, it's a prototype, and it's of course only for military applications would be the end idea, but it's a laboratory prototype, and it works quite well for as blocky as that imagery is. That's very good for through-wall radar. If you look at a lot of the other systems out there, it's good. So.
What about this? So this is part of the course with I think, but it has the Wi-Fi transmitters. Is that right? The phased array. Is that something different than the coffee can?
Yeah. So that was there was a good question. Now, we had the coffee can course was successful. So Lincoln Laboratory wanted to have another radar course, and so I proposed. Let's run the coffee can again, and let's kick it up a notch. Let's build phased array radar systems.
Cool.
Yeah, and what we did was we.
So what is? I don't know what that is. Sorry. What's phased array?
It's a radar that has multiple antenna elements, and let's say for example, like the big red radars that you see at airports that look for the aircraft. The FAA radars. I think it's the ASR 9.
Yeah. That
radar is what's called a real aperture. It has this big huge dish and it spins and it scans the horizon. Now, a phased array radar is something like you'd see on the Aegis system. The Aegis weapon system, which is in all of our destroyers. You see those flat panels on the front.
Mm-hmm.
You see them? Yeah. Those are phased arrays. Now, those things can scan in all directions like that big red FAA radar can, except they do it digitally.
Using beamforming technology, which is pretty advanced.
It is, yes.
Yeah, I've worked on beamforming underwater sonar stuff, and that requires massive FPGAs, massive parallel processing. That's one of the beamforming is one of your traditional uses for your $10,000 high-end FPGA chips.
Yeah.
It's really advanced stuff.
So what we wanted to do at MIT was we wanted to have a course on phased array radar. And so instead of doing it with $10,000 FPGAs, we were going to make phased array radars out of pegboard and Wi-Fi antennas.
Of course, as you do. Explain how that works.
Well, what we did was we succeeded. Okay, and it worked.
Okay.
We had the class, and it was a big hit. So what we did was I designed the radar with another guy, Lincoln, Brad Perry, and we found these really low-cost Wi-Fi antennas, patch antennas, and so we bought a few and measured them at the laboratory and realized, this will work. It's the only thing we can get, so it's going to have to work. So many of my designs there's no spec. It's like, let's just see what we can do and make it work, So anyway, we found these antennas. We came up with an antenna layout that would allow us to operate in what's called a switched array mode, where we took a coffee can radar and removed the coffee cans. Instead of plugging the radar's transmit and receive ports to coffee cans, we plugged into antenna switches, a 4-port switch for transmit, a 4-port switch for receive, and then each 4-port switch was connected to 4 Wi-Fi antennas, and we placed them in such a way that we could get half a wavelength virtual aperture spacing. So we switched. Let me back up a little bit. We'd transmit on one, receive on another, then switch and transmit on a different one, receive on a different one. We would do several combinations of antennas. I think it was like...
So was that like a MIMO system?
Yeah, it was
MIMO.
Like it was a MIMO system. It was time division multiplex. We didn't transmit simultaneously.
Okay. So MIMO being multiple input, multiple output.
Correct.
For people that don't know that.
So it was MIMO. We used a LabVIEW little USB controller to toggle all the antenna switches and pull in the pulses. And we had a real-time phased array radar system of a range of about 100 meters. And you could watch people walk around the Common at MIT or wherever. You could watch cars drive by with the thing.
Awesome.
It was really cool.
Well, you can also do that with a camera, and your own eyes.
Yeah, that's true.
Yeah. But it's not as cool, right?
Hey, what if it was foggy?
I
What if it was foggy?
Yeah, exactly.
That's right.
Oh, boy.
So, you didn't happen to use the Edis research stuff, did you?
No.
Because we've had Matt Edis on the show before.
No, we didn't.
Oh, okay.
I've looked at that before for the radar problem, and the trouble I've run into, and some people have taken the radar courses have tried to use it for the coffee can radar. The problem we run into is triggering and timing. The radar is all about timing. You transmit something at a known time, and you receive, at a known delay from that time. So that is stuff sent to.
No Linux then.
It tends to favor streaming. It's radio, so it's all streaming, and so I think maybe you could get that to work with some clever hacks or something. I'm sure someone can get it to work, but it wasn't us. We didn't have enough time to figure it out and do it. So.
There's a interesting question from Erison, who's one of our listeners. Do you know of any reconfigurable antenna technology, perhaps built using MEMS technology? He's looking for something, the physical equivalent of an FPGA for antennas.
Yes, I know about that. They're called self-structuring antennas.
Ooh.
And they are still in the academic and military space, and the idea is you have this antenna and you have lots of elements on it, okay? And then you have little switches that add those elements or remove the elements, and you use a
elements
algorithm.
As in fractal elements, perhaps?
No, just
regular
wires.
Right, okay.
Imagine
regular,
a large printed board, maybe 12 by 12, and you have all these wires in like a grid or some sort of array. And where each one meets, you have a switch. And you put that
expensive
in,
RF switches, all that kind of thing.
Yeah.
Got it. Yeah.
The idea is that you could take this antenna and throw it on anything, and it would self-structure for optimum, because we know that if you put an antenna on like a car or aircraft, it's different for every aircraft. We know this from the military side of things. Every time you put a new antenna on an airplane, you basically have to make a special antenna for every single airplane. Because the skin of the airplane goofs up the antenna pattern.
Yep.
Right.
So it's that's what airplanes. Everything's expensive in the aircraft world.
Right. So technically, that pretty much exists at the academic level. And
Yes, it
and
does.
antenna-based FPGA.
Yes. There's a
Wow.
gentleman who worked in my lab at Michigan State who built one, and it worked quite well. His dissertation was on that exact problem.
There you go.
Yeah. So if he
like he
emails
asked
me,
the right place,
I
huh?
can put him in touch with this guy. So
Sweet.
yeah.
Have you worked on fractal antennas? Have you done anything on those? Because they're obviously, what have made our miniature mobile phones and everything these days possible.
I haven't touched them. My concern is just my interest in antennas extends to what do I need to do to make this radar work?
Got it.
And then I stop right there. So I've designed antennas before, but only to make the radars work. And then I have a gist of how they work, and then that's it. Got to move on to the next problem.
I love it.
That's great.
Who's got time for everything?
It sounds like you're a hacker trapped in a professor's body, Greg. I hope that sounds like a compliment,
No, it
because it
sounds
really
right,
is.
though.
It's meant to
It's
be.
very accurate, I think.
It really is. What is your actual research area? I mean, it's in the radar systems area? I mean, is it?
Well, I kind of, I got into the radar because I worked at a company building radars when I was in high school, so I thought it would be cool. And then in grad school, I taught myself how to build imaging radars, and I made a series of 5 different imaging radar systems. In my garage, I had a microwave lab in my basement, and I had a milling machine in my garage, a Bridgeport. I could turn out anything in that garage at my house in grad school. But the reason why I did that is I just thought it was fun. I ended up getting I was studying applied electromagnetics, and I was very much interested in the applied aspect of electromagnetics. So my dissertation topic, I actually got the funding myself for the dissertation topic. It was funded by the Naval Research Lab in Washington, D.C. I met the head of the radar division at a conference. And at conferences, I like to go, hang out and chit-chat with everybody and see what they're doing, because it's fun. And this guy
that's
said,
the way to do it,
hey,
man.
we're trying to look at this through-wall problem. We've been struggling, and do you want to, you sound like you've got some really good experience building these radars in your garage. Do you want to give it a shot? So I said, yeah, why not? So, they funded my dissertation, which was on through-wall radar. Then later on, we brought that work into Lincoln Lab and made the very advanced through-wall system, which you see online.
Do you think, you said they funded it, do you think you would have been able to do it if they didn't fund it?
Yeah, absolutely. I think I spent, to build so I had to develop, as part of the dissertation, I built a model to see if it's even possible to get the right SNR to actually form imagery and so on and so forth. So I made a model. Then I came up with an unusual radar architecture that would facilitate low peak power pulses and long waveforms. So I was transmitting 10 millisecond long chirps into the wall and being able to pull them out, which is difficult because most of your energy just bounces right off the wall and then saturates your receiver, deafens your receiver, and distorts everything. Yeah. So that's what you have to fight, is that problem. So therefore, most people who approach the through-wall problem look at it in terms of an academic sense. They say, well, if I'm going to saturate my receiver with a big, long waveform, I'm going to send a short 2 nanosecond waveform. Well, what happens is if you send a 2 nanosecond waveform, now you got to dump 10 kilowatts into that 2 nanosecond waveform to get in and out of that wall.
Right.
Yeah.
Well, my system's in grad.
Then the wall explodes.
Yeah, no. Well, it's fine. It doesn't explode, but 10 kilowatts, now you need a TWT amplifier. You need all this expensive crap to make that happen.
Right.
The infrastructure goes way up, okay? And not only that, to digitize a 2 nanosecond impulse, you need a good 4 gigasamples per second or better digitizer. And the performance of those digitizers are not as good as the 100 kilosamples per second digitizers. And so, so the system becomes unbearably complicated. And you also have to swallow a lot of data. So it's very difficult to do real-time processing and real-time imaging with that kind of data coming in. Even today it does. So my approach was, oh, no, you know what? Everyone's doing that in that field, the field of through-wall radar. Everyone seems to be going the impulse route. I'm going to go the opposite. I'm going to send a really long CW, FMCW chirp at the wall, and I'm going to figure out a way to reject the flash, the reflected signal off the wall itself, and only receive what's behind the wall, only send what's behind the wall to my digitizer. And I did that.
And how do you do that? Do you just shut it off during a time? You shut your receiver off during a time period so you don't saturate it, or what?
No, it's always on. What I did was I first of all, I used a wide dynamic range front end. And what often happens in radar systems is the electronics often have more dynamic range than the digitizers. So you're usually managing digitizer dynamic range. So I had a wide dynamic range front end that can just take it all in, no problem. And what I did was in the IF, I down convert to 10.7 megahertz, and there I used a trick. I used what's called a crystal filter, which is what you use in a ham radio single sideband transceiver. I put a crystal filter there. The crystal
sounds pretty obvious, actually.
It does, doesn't it?
With hindsight, right?
Yeah, it costs like $5 from DigiKey.
Yeah.
That's where I ordered from. It was from DigiKey, and I threw that in there. And
that's awesome.
when I chirp the radar, there's a function of the rate which you chirp and blah 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 blah. So when the smoke clears on the map, what happens is the crystal filter acts like a range gate. When you have an FMCW radar, range to target is proportional to beat frequency on the output of your front end of your radar. So you multiply your transmit chirp by what you're receiving all the time. And so
fascinating.
The product ends up becoming a frequency difference on the order of kilohertz, okay? 10, 20, 30 kilohertz. So let's say there's something 50 feet away, it comes in at 10 kilohertz, and then and now you have something 100 feet away, shows up at 20 kilohertz, for example. So what I did was
interesting. So it's almost a range to frequency converter.
It is, yes, precisely. Yeah.
Wow.
And this technology has been around since the 1930s. This is how radar altimeters were created in the 30s. They
of course.
Yeah,
Yep.
Delta F. Delta F.
Yeah, that's right. That's probably how they landed that rover on Mars too. They had the radar pinging the surface, and they.
Oh, I'm sure. Yeah, they probably had some kind of radar like that to close the loop on that. I'm sure they did. Yeah. And they're so close, they might be forced to that solution. I don't know. Maybe it was an impulse, but it could have been FMCW. Most likely because that's historically radar altimeters are FMCW.
Right.
So now you have frequency is proportional to range. Well, I want to filter out the frequencies that correspond to the wall and pass the frequencies that correspond to the people 10 feet behind the wall.
That's easy.
That's the problem, right?
Well, it doesn't sound that hard.
It's not when you think about it from this perspective, from a systems level.
Right.
So I said, well, they have these, my ham radio in the basement's got this amazing thing called a crystal filter in it. It's been around since the 30s. And it really does a good job of rejecting everything outside of its passband. It is very, very tight characteristics. So I thought,
steep curves and either side. So it's bandpass filter.
Nice and steep. Very, very steep.
Yep.
So I bought one from DigiKey, and I architected the radar so that instead of converting down to 10 kilohertz, I converted to 10.7 megahertz. Okay, so I can feed that baseband signal through one of these crystal filters. And what I did was I adjusted the LO on the radar so that
local oscillator, folks.
The local oscillator, so that let's say the wall was coming in at 15 kilohertz and the people behind it are coming at 20 kilohertz. I set it up so that the wall would be buried in the noise and the people would be passed through. And then I down convert to baseband after that and digitize with a 200 kilosamples per second 16-bit A to D. So I had a really low bandwidth A to D, very low bit count, very small amounts of data. And
so you can get massive dynamic range on your ADC there.
Yes, yeah.
Cheaply and easily.
Right. And now with only 1 milliwatt of RF transmit power, I was looking through 4-inch solid concrete walls, and I could see a Coke can behind the concrete wall moving.
Wow. With 1 milliwatt.
1 milliwatt. And that was in my garage in East Lansing.
And this brings us to a question from Tom Circuit, he calls himself. He wants to learn about low power, sub 100 milliwatt radar systems, but he finds that most of the literature is high power, long distance military.
Yeah, it's unapplicable.
Stuff.
It's totally unapplicable.
We should mention that's
with Lost
Tom
Chris.
Laments of the. Sorry, that's Tom Laments of that was formerly on the show. So.
Oh, is it? Okay.
I thought that was interesting
right.
too.
He's calling himself Tom Circuit on Reddit. Okay.
Yeah, I know him. So it's a good question. So most radar books are entirely theoretical. You almost never see design examples, and there are some good ones though that I can recommend. Like Intro to Airborne Radar is probably one of the best. But they're long range far field radars, and when you get down to the milliwatt level, your radar is often in the near field, so you have to account for that sometimes, especially if you're making a phased array radar. And you have to use unusual architectures. You're not pulsing a 100 kilowatt pulse anymore. You're probably CW because you don't have enough. Otherwise you have to pulse a nanosecond or something, and that gets tough to analyze. So yeah, I'm writing a book on small and short range radars to fill that gap. So it will be the only book on small and short range radars when it comes out.
Wow, there you go. And how's that going, by the way? Because we've talked about writing books on here, because I've been, offered deals to write books and stuff, and yeah.
I signed the contract a long time ago, back in 2010, and we're creeping along.
And we're still going. Okay, there you go, folks. More confirmation that you can't write a book in under a year.
No. It's so much. And if you're trying to get a startup off the ground, there's really no time for the book. Yeah, we're getting a few pages done a week, and I could talk to Tom and send him some of the. I can give him a preview if it helps him. So.
Oh, there you go.
Yeah.
Awesome. So you've got a deal through a book publisher?
Yeah, CRC Press. Yeah.
Oh, there you go.
Yeah.
Look out for that, folks.
Look out for it.
Estimated time? How close are you?
Gosh, I think my deadline is in the winter, but it might slide a little bit.
Winter of what year?
2013.
Oh boy.
Well, subscribe to my blog, and then you'll know it. I'll blog extensively on it when it does come out.
Blog it to death.
I will blog it to death, and the book is unique in that it shows design examples. So we talk about the theory, of course, and we show in the book I show how to characterize the expected performance of various small radar systems, and then I show working example after working example after working example. Each one has a bill of material with it. It's got all schematics and data. I'll put on the website measured data that you can process, MATLAB scripts to process the data, and a YouTube video showing you that radar in action. And the data acquired during that YouTube video will be on the website. So that's the plan, and it's moving forward quite well.
I think Tom's salivating at the moment.
Yes. But unfortunately, we're a little behind, but hopefully we'll get it out there eventually. But that's the vision for the book, and we'll make it happen.
Mm-hmm. What's the target market for this book?
People like Tom.
Right. Are you hoping to get it used as a course text or something? Is that an intention? No,
that'd be nice. I think it could be, but I think that the objective here is it's really filling a gap. When I learned how to build these small imaging radar sensors, I had the same problem Tom had. I'd get Skolnick's Radar Handbook, which is an excellent, amazing book, by the way. But I would find a lot of its material is unapplicable to what I was trying to do in my backyard.
Right.
So it's just like the radar class. I wanted to write a book about radar, how I would have wanted to learn it myself.
And that's the way all the best things come about. What would I want? And then, boom, you produce that. And then other people go, oh, that's what I want too. Yeah. And, it's the best way to do it.
Yeah. And hopefully it'll fill that void and, get more people into this this amazing and interesting hobby that can turn professional.
So how big would you say? I mean, like radar seems like it's still pretty niche for for military and aerospace applications. Are you seeing it in other spaces? Are you seeing interest from other industries?
Little bit. You see it. Automotive uses it here and there for blind spot detection and automatic cruise control and stuff. And of course, you have the ubiquitous door opening thing that you see at the big box stores. You walk up to the door and it opens. That's because there's a small radar up there.
Oh, isn't infrared? I thought that was all the infrared IR movement detector.
They're usually radar.
Really?
Yeah.
It's interesting.
Yeah. I could have sworn that, though. I know you can get dual types of alarms now that are combination infrared and sort of radar-like. I'm probably talking out my ass here, but you can get like these dual alarm sensors, and I thought that's probably what they were at best.
No, oftentimes they're usually what's called a gunplexer, which is it's a type of microwave module. It's been around since the 60s, and it consists of two diodes and a ferromagnetic circulator. And what it is basically like a radar TR module, very cheap, and it transmits a 10 milliwatt CW signal, and there's a little mixer diode right there next to the gun diode, which is oscillating, and it always downconverts whatever it is reflected to it.
Well, that's going to really make the paranoid tin hat wearers even more paranoid.
Yeah, they're everywhere.
Go into the local... I'm not walking in that shopping centre. He's pointing a radar at me.
Yeah, they do.
Phone, RFID.
And I've taken them apart before. Stanley makes one, and that's the one you see everywhere. If you look at the name, it's usually the Stanley one. It's really nice, and you could then you can buy one. Probably, I'm sure you could buy one on Amazon.
Is there a way we can mess with
What's
one? Is there a way to like hack with them and mess with them, like to try and get them from a long distance?
You could. I'm sure you could. I bet you can jam it from across the parking lot. Just have it open the door.
Ah, right. There's a fun project, folks.
Yeah, I'm sure you can do it. I have no doubt it's possible.
Aha! You call it the radar be gone.
The radar be gone.
There you go.
If you're one of those people that wants to waste the heat, of the big, you can, if you want to like bankrupt a big box store by wasting heat and just opening the doors all the time, there you go.
Oh, right, yeah. There you go. Yeah, of course, yeah.
Or you could be like a James Bond bad guy where that's like or like a Simpsons bad guy where that's your plan for taking over the world. You heat the world
to jam
by
those little radars.
Every door going
So
open.
please tell us, how do we jam such a radar?
Gosh, I got to think about that.
I want to know because I want to try it.
It'd
be awesome.
There'd be a couple ways of doing it. I think that the most difficult way would be to try to lock onto its frequency, phase lock to it.
No. I just want to know. I just spew something out.
What you'd have to do then is probably the easiest way to do is to buy one of those things,
right,
on Amazon.com and rip it apart, take out the gunplexer, and then make a circuit that deviates the bias voltage for the little gun diode, and that'll cause it to modulate in frequency back and forth, and that'd probably get it.
Novel, but I think overcomplicated. It's got to be a simpler way. Come on.
Oh, there's no simpler way than that.
Come on, Dave.
Come on, that's your PhD talking. Come on, I want the ham hacker talking here.
Maybe what you could do then, ham hacker way. Let's think about this. Oh, you know what? I just thought of it.
Here you go, folks. See, well, once he puts on that ham hacker hat,
you know what?
I saw this thing. Comes in there.
I saw this thing at a lake house few months ago.
What's a lake house? Sorry,
just
I have
a
no idea
cottage on the lake.
Oh, a literal lake house. Okay, right.
And these people had these little solar-powered lighthouses on their front, and right where their boat ramp was, so they can come home and see where their boat ramp is.
Okay.
And the solar-powered lighthouses were neat in that they had an LED light, of course, which is ubiquitous with solar lights, but they also had they had a motor in there that would rotate a mirror around the LED, so it actually rotated like a police light or something. So what I would do is get one of those things, okay, and try to retrofit a tinfoil hat or some sort of larger reflector on there, and have it rotate all the time, and it'll always be fooling the Doppler radar.
There you go.
Yeah.
Do you think there's any radar application? Like we're seeing, Google just got that bill passed to have driverless cars in California. Yeah. Is that part of is that going to be using radar
Probably.
for like collision detection?
Yeah. I'm sure it is.
Okay. So there is a pretty practical application for, like widespread stuff, huh? I mean, like it's not necessarily just seeing through walls now, or detecting when
what
airplanes
it does
are
is
coming.
radar
it's like,
gives you
hey,
range.
a car's coming
it
towards
gives
me.
you range, unambiguously. Here's the range and angle of something, and that's very valuable. If you have like optics and cameras and things, and there's some algorithm that has to take place to sort of back out the range. But the radar, it's given without any thinking, really, necessarily.
But cars are going very fast, so how fast can you detect the rate of change?
Oh,
which
instantly.
is where instantly, right?
Yeah, really.
So
quick.
you can be traveling 100 kilometers an hour. Sorry, got to speak Australian here. 100 kilometers an hour head on.
What's that mean?
To another car.
Kilometers?
I don't know. That's about 60 miles
60 miles an hour.
Oh,
you could be heading 60 miles an hour head on. So two cars heading smack into each other 60
This is a
miles an
math
hour.
problem.
Yeah, it can still detect
Two
that.
cars leave
Yeah,
from
yeah,
their
well,
houses
think about
at
it.
9 a.m.
Fighter jet radars, right? Those
true.
They go a lot faster than 60 miles an hour.
Oh, yeah.
Yeah, there you go.
Okay. Fine.
Yeah, there's no reason why you couldn't do it.
Does that work at any frequency, really?
Yeah,
Any
it just
frequency
depends how
radar?
you process and the pulse,
You're right.
the rate at which you pulse the radar and the your waveforms and so on and so forth. But absolutely, you should be able to pull out range and then some sort of vector of what the target's doing pretty easily. Yeah.
Okay.
So, well, if every car on the road has this at some point, does that mean that it'll start like flooding the spectrum, or is it such narrow band signals that it really, and they're sweeping so much
That's
it
a good
won't really
question.
matter?
I would say, well, I'll give you a working example. Now, the MIT radar class, we would have an entire room of 30 of these coffee can radars going at the same time.
Oh, yeah.
They share the band with Wi-Fi, and everyone has a laptop on Wi-Fi. And we had no problems ranging people down the hallway and in the classroom itself. So
Right.
they're chirping radars.
Yeah, that's a good measure.
You got to be nice and close to get to cause interference with each other. So it's funny if you're ever on a boat and you have the marine radar going, you almost never see interference from other marine radars. They're all on. So a lot of things have to, the moons really have to align to get to have the radars jam each other. But that being said, yes, they can interfere with each other, but you have a few things working in your favor. For one, the frequencies have to line up very closely. So if it's an FM CW radar like my radars, and they're only interested in 0 to 100 kilohertz away from the car, and let's say a radar is chirping, but its chirp is 10 megahertz away from yours, its slope, meaning its slope is 10 megahertz advanced or retarded from yours, you're not going to hear it.
Mm-hmm.
So the probabilities of the chirp lining up are pretty low, and then also the beam widths too. So like cars, are stacked up on top of traffic. I would think that their beam width alone would probably be limited. You don't have to look at it in terms of the isotropic case where it's free space all around. You can have some caveats in this, but it has to be looked at for sure.
Because even if the odds are 1,000,000 to 1 of it happening,
you got to know.
You got a million cars on the road. You've got an accident every day.
Happen,
I mean,
I think you'd have to have some sort of the radar would have to be smart in that you would have to do a receive pulse every now and then where it doesn't transmit and it just sweeps its own receiver and checks the spectrum. And if it sees something else, then it starts blanking that. And these radars are going to be, pinging. They're going to be pulsing at such high rates that they can spend a pulse every now and then checking the spectrum. I see no reason why the spectrum cannot be dynamically allocated. And I can think of 10 ways to do it. I mean, it's very doable. We just have to be willing to take a few risks and work out the bugs, but it can be done.
Man, bloody radar everywhere. I'm going to have to start wearing tinfoil underwear soon.
Then we'll definitely see you then.
They'll know exactly where you are, Dave. So what about this, did you guys already mention the startup? I know I've been dropping in and out of here, but have you mentioned the startup yet?
Yeah.
That you're working on?
Where we're hiring.
Yes.
Oh, you started with that, right?
Yes, we're hiring.
Yeah.
So, what is your experience like, though, at a startup? Is this your first startup?
It's my first, yeah.
And but you're one of like half a dozen. I'm having a look at the people here. You've got like a dozen people working there already,
6.
right? So it's a well-funded startup.
It's very well-funded. We have more money than time.
Right, there you go, folks. Turn up with your
you guys
PCB in hand and you'll get a wad of cash.
Prize.
Yeah, we're going for the tricorder prize, yeah.
That's great.
And we
had talked about that previously.
But why? What's the prize? Are you going for the prize money or are you going for the fame?
For the fame, not the prize money.
Right. So how do how does your investor feel about that? Because usually startups are like, we want a return on our investment. Screw the fame stuff. We just want our money back.
Our investor,
well, the fame makes more money, dude.
Well, not necessarily.
Oh, please! If you win SpaceX won the X Prize, didn't they?
Yeah,
didn't they win the SpaceX Prize? Yeah,
but they were putting freaking rockets into space, man.
Yeah, that's right.
They were putting rockets, not making it.
What did they get for that?
Don't listen to Dave. Don't listen to Dave.
What did they get for putting rocks? $1 million or something? What was the prize?
I think it's 10. I think most X Prizes
That can't be
10.
enough for the rockets, man.
No, it's not. No, they spent
that's
50
like fuel.
times that.
Yeah, they burned 10 million of fuel just getting halfway up there.
Yeah.
Yeah.
Whatever happened to the Lunar X Prize? Or
There
whatever
was
it was
one.
called. That
Really?
Yeah, you can. You are the first person to land a rover on the moon.
Okay, a rover.
And transmit a high-def video back wins the 10 million, 30 million bucks or whatever it was.
That's interesting.
It seemed to just dissipate. It was a big fanfare.
Sounds like a microwave antenna. Maybe that's another thing you guys should do. Team up with SpaceX.
It seems doable. It seems doable. I mean, the bar is not that high. It just has to give you at least one picture, and then it dies, right?
Well, exactly. I did like one team's shot at it. Their theory behind it was that, we'll do, instead of putting all our eggs in one basket and doing the one mission, we'll do 20 missions that cost $50,000 each.
Yeah, that's the way to do
and
it.
one of them's bound to work.
Yeah,
right?
and each mission they dump like 1,000 radio-controlled Tonka trucks come spewing out of their spacecraft above the lunar surface with those free, those free digital cameras you get like $10 digital camera from the drugstore. Each one has one of those duct taped to it.
That's like the Million Monkeys idea, right? You just eventually it's got to work.
One of these rovers, these Tonka trucks, it's gonna bounce off the moon and come back to Earth. That's how you retrieve the picture. It doesn't transmit it or anything.
That's right.
That's how I would do it.
So your experience as a startup is probably wonderful because you're actually getting paid.
Yes.
As opposed to a lot of people I know doing their startup, well, they're just, starving and eating dog food.
Yes. Our investor has no problem paying what he needs to get the best people in the world to join us.
That's the way to do it, folks.
Mm-hmm.
Yep. Make sure somebody else pays for your dream.
Apologize,
right?
That's right, yes.
Did you guys already talk about what it's about? Because that's the thing I didn't understand is, what are you guys doing?
We said what it's not about.
Yeah.
We said it's not
is
about,
that the main thing
it's not about social media.
No, it's not Web 2.0.
You're actually building shit.
We're building a lot of
How
stuff.
novel. How dare you be a startup
it's very
and actually
risky.
build something?
It's risky.
Well, hardware is so awesome.
It is. We've built 3 prototypes already since I started in last November. Yeah. And we're working on a tech demo, and it should be. It's a wild ride. We're actually executing very, very well. So far, so good. But
and we talked about how
again we don't know what it is. I'm not like
we're not allowed to say. It's all hush hush.
Yeah,
okay.
Unfortunately, I wish I could. Maybe in the winter I could talk more about it and reveal some more, but I just can't right
it's
now.
All shades it's all shades of Valve here, Chris. And I did poke fun that
funny.
he hadn't been poached by Valve yet. So yet.
Oh yeah. Well, once he's done with this.
Yeah.
But no, I mean that's that's an interesting case though, because with startups and a lot of other things, like even funding situations, sometimes people get funded just based on the people, right? And I could see very easily if I was an eligible hired person that wants to get hired for a startup, that based on Greg's work alone, it would be something I would want to do just because he's doing it, right? I mean that's the kind of thing that those are good situations because they're exciting. You have to take a little leap of faith, but whatever.
Well,
that's
hey,
good.
if anyone out there wants to join us who can code FPGAs and design boards, send me an email by all means, and I'll look at every single email you send. So.
And they will outbid Valve.
Totally do that too.
Yes, we will outbid Valve. Actually, we have the means to outbid Valve. No question about it.
Are you doing Verilog or VHDL?
Verilog is our preference.
East
Yeah,
Coast. Every time.
You picked the wrong one. You picked the wrong horse.
I know. Seriously, Midwest gets screwed. Especially, like with all the military stuff.
Yeah.
So. Anyways.
Yeah.
Verilog.
I'm sure we have listeners out
That's
there
cool.
who will, no doubt.
Should
Don't send a resume, folks, and that's what we talked about. Don't send a resume, send a board.
send pictures of your board.
Or photos of you with your board.
Yes.
Yep.
Should I give my email address out now, or do we put it in the show?
We'll put it in the show notes.
Okay,
in the show
good.
notes.
Yes.
Yep.
Email me for just please. We could use some people, and it's hard to find those people who are really good. They're very tough to.
Yeah.
I almost think that they're the underappreciated lot, where they're kind of at some giant company, designing boards or coding the FPGAs, and no one knows who they are because they're not publishing papers and stuff. It's easy to find PhDs because they're out on the scene, they're publishing. But
right, it's a career move to be self promoting, right?
Yeah.
It's whereas
That's
if you're doing
how
FPGAs,
everyone
you
got
might be
hired
working
at
for a big
Valve,
company.
right? Because they were all bloggers. They were all putting their work out there.
yeah.
And that's how they were found.
You got to put your work out there these days.
Exactly.
Yeah. But for all of those who haven't but have done cool stuff, send me a note. We want to see what you've done. We find this exciting. We're trying to build up a team to fab boards very, very quickly.
Yeah. Oh, that is fun.
I
like
can't
that a lot.
wait. I hope to get involved so I can learn how to do this.
So what's stopping you from? I mean, I'm sure it's a time thing now, but I mean, you could very easily just go buy, Eagle or KiCad, whatever else, right? You could just.
That's a good question. You know what? I never I never build something just for the purpose of building it. I want to learn something from it, and it's part of some bigger thing. So, for example, the ham radio that I built recently, the 6 and 2 meter transceiver, they're all dead bug or or perf board. And I couldn't justify the time to learn that for that radio. I just couldn't.
And a circuit board is just another means to the end of producing something and learning.
Yeah,
right?
I could still get there without the board.
Well, and also,
it's like some people
and your
like
first
like
board
me now.
being RF.
It would have been RF too.
Well, yeah. Well, it's like, people ask me, why don't I make my own boards at home anymore? Well, because it's just a means to an end of getting the board that I want. Right. Why waste my time doing that? I don't care anymore,
but eventually that argument, eventually you have to, I always do that too, right? I say the same thing, but then, 50 boards in, I'm like, man, I should have done that 50 boards ago. It's the same thing. I mean, I understand.
You don't want to spend your time
right.
manufacturing a board. You just want to design the board, send the file out, and bingo, magically it comes back one day. Right. That's you don't want to waste time doing that. And I can imagine that's the same for you, Greg.
Well, oftentimes my career objectives have been to prove a concept. As soon as I've proven the concept, then I move on to the next project. Yeah. So nothing's volume. Everything I've done is one-off.
So you've never finished anything. You've never taken it through to volume production.
Nice,
you're one of these 90% engineers.
That's right.
like
right.
us. Yeah. I'm finished playing with that. Next.
That's right. Well, hey, once it's done, I got the 23 tube home theater. Okay, I'm done. That works. Move on to the next thing. Let's build this ham radio now. Let's build this through-wall radar. All right, it works. What's the next thing?
Yeah. Well, that's interesting as you move into DFM situations. I'm sure you'll learn a lot at that point, right? That's
DFM?
Just design for manufacturing type stuff.
Man, see, I don't even know what that means. That's how bad I am.
Yeah. Oh, sorry.
I'm going to have to learn. Yeah. That's why I need help.
Wow, that's just sorry, it's an acronym.
That's why we need people to join our company to help us with these things. I don't even know what DFM means. See how much help we need?
And then you'll find out, by not having anyone in the company who knows what DFM means, you'll find out that doing a hardware startup's probably not the best idea. Because it's a pain in the ass getting something manufactured. Oh, boy.
Did you guys already talk about the preamp you built, the Buddy Guy show thing?
No, we haven't. In fact, no. What
was that? I mean,
well, it's sitting in front of me right now, actually.
Really?
Yeah. It's
how big was it?
Well, the preamp itself was pretty tiny. I'm looking at it's probably about 4 by 3 by an inch and a half tall, plus 2 tubes sticking out of the top and a transformer for the high voltage supply. And the knobs and things.
Now, it's obligatory that the tubes have to stick out the top so you can see the glow, right?
Oh, yeah, absolutely.
It's obligatory.
Yes.
Yep.
Yeah.
There's absolutely no point building a valve bit of gear unless you can see the tubes.
I don't see the point, personally. Yeah, we got to have them out there.
Wank factor, folks. There has to be a wank factor.
Right.
And you may as well put the transformer out there, too. Because that looks cool. And then I thought, for aesthetics, I put the knobs right next to the tubes. Right between them, even. So the gain and the pre and post gain are right there. So it kind of looks like an old school prototype of some kind, but it's got a good finished look to it, a nice military look to it.
So what was the story behind actually getting caught with this thing?
Well, so I built this thing because a friend of mine was a DJ at the Michigan State's radio station, the Impact, they have a web radio. It's a great radio station if you're into independent music, and I think it was on Wednesdays they have this program, and they still have it. It's called Accidental Blues, and they play all these blues, songs and whatnot. And this guy, his name was Ryan Noyes. He's a really cool guy, and he knew the blues so well. He'd trade bootlegs with people. And this is back in when you would post your list on your website, your Web 1.0.
Oh yeah,
GeoCities website.
Yeah,
and then you get an email saying, "I'll trade you this CD for a copy of this CD."
That's how things were pirated back in the day, folks.
The high fidelity tapes, even the
reels. No, we were past that at this point, but not much further past that.
Or mini disc. Mini disc was another one that was fun.
Well, in fact, we use a mini disc recorder for the show. That's what we used.
Oh, okay.
Yeah.
Nice.
So we were well within the mini disc era. And
so, did you have this high volt? I mean, you did a boost converter or what?
No, it was real simple. It was just a 555 timer, the ubiquitous 555, and it fed into a 1-watt audio amplifier IC, which fed the secondary of an old military audio output transformer. So it fed into the 8-ohm side,
Oh,
and then out the 3300 ohm side came, a couple hundred volts.
yeah.
And it was
Step that
perfect.
shit up.
And you crank up the frequency so it's really high, so you don't hear the hum when you're recording.
Yeah.
Mm-hmm.
And that's easy to filter it with small capacitors, because if you had to use the big, electrolytics, there's no room. You couldn't cram them in the preamp.
Yeah.
And so we built that. It actually was on the front cover of Audio Express magazine. So we built this thing. I built it because my buddy, who was the DJ, wanted to record this Buddy Guy show in Chicago at Buddy Guy's Legends Bar. And so we had this, bunch of 21, 22-year-old college guys, road trip to record the show. And, lots of things seem like good ideas when you're that age. And we get in the car, and we're going down to Chicago, 4-hour drive. We're like, yeah, it's going to be great. And I show everyone the preamp, and everyone's just really fired up about the preamp. And my friend's like, this is going to be awesome. This sounds so good. I got this lapel microphone. It's like a really high-end one. I borrowed it from the station. It's like a $500 mic. I'm like, yeah, great. This is perfect. And then here it's got this nice little thin lapel wire, that goes between your clothes. It's really thin. Then it's got this, this big plug on the back or whatever, the 3-prong mic plug, whatever you call those.
Oh, XLR, yeah.
XLR. And then it's got to plug into this 20-foot roll of half-inch cable to go to this other weird adapter that's 6 inches long, that has a transformer in it to plug into the tube preamp, because I had high impedance 50K input. I wouldn't talk to the XLR. That was our first problem. All right, so we're like, okay, whatever. And so then I'm like, okay, but whatever we do, guys, we have to leave room for the 8 AA batteries that hang off on a separate battery pack off the back of this damn thing. I'm like, okay, fine, so we put this whole thing together. It ends up being, about 2 bread boxes in size of cable and batteries and crap,
Walk in looking like a transformer.
I know. Well, good thing it was before September 11th. They would have thought we were terrorists or something, with all this wiring and
all
stuff.
strapped.
Yeah, just all strapped in there, trying to be covert. So my buddy's like, we got to do this. I'm going to throw it in a backpack. We'll put some dirty underwear on top of it and some clothes. And it's just a bar. They're not going to check our backpack. So we go in there, and then they didn't care. And so we went in with the backpack. And we sat up underneath a PA speaker, and we showed up like 3 hours early before Buddy Guy went on. So we decided that, we're 21, 22, 23-year-old males from a Big Ten university. We decided to have a few libations before the show. And many rounds later, my friend Ryan forgets how to turn on the preamp.
Oh, no.
So when we go to set the levels, because you couldn't leave it on the whole time, 3 hours before the show, we'd kill the batteries because we got tubes there.
Right.
You can't leave those filaments lit. They'll just suck the batteries down. So we left it off. And he couldn't turn it on, and then one of the bouncers saw him and grabbed him and the backpack and yanked my friend away to a back room where they interrogated him about recording the show, because I don't even know why they even care, but they did. And they kicked him out onto the streets of Chicago in January, freezing cold out there, like 10 below zero.
Oh, jeez.
And so we're standing there, and my buddies and I who are left, and we were like, what should we do? Our friend Ryan, brought us down here for this. But we have his pitcher of beer with us. He gave it to us when he got yanked out. And we have his $25 he gave us to go to the bar to pick up more drinks. So I said, you know what? I say we stay here and we drink his beer and we watch the show, because that's what Ryan would have wanted.
That's what he would have wanted.
Yes. And we'll spend his money, too, at the bar, because that's what Ryan would have wanted. And that's what we did.
He got hypothermia and whatever.
He was freezing out there.
Oh, no.
Yeah, it was rough.
Oh, God.
It was rough. We had to come back the next morning to pick up the recording rig.
They didn't break it or
They
anything?
didn't give it back to us.
Oh.
No, they didn't. And we went up to the door to ask for it back. They're like, which one's yours? Because 2 other guys got busted for doing that that night.
They weren't nearly as nice.
And no. And so we told them it was the tube rig. And they're like, yeah, oh, you guys are the tube rig. Wow, that was cool. So anyway, that was fun.
Oh, that's a great
So
story.
that's what happened with that thing.
Now, you're a ham, aren't you?
Yeah, yeah.
And you've seen this video I sent you before the show?
Oh, yeah, those guys,
we'll
man.
post this link in of a guy called Julie Kentwell. He's an Australian here, and you agree? Do you agree with his quote from this video where he says there are two types of ham shacks: those that are an absolute pigsty and those where nothing happens?
I think that's fairly accurate. And there are those with appliance radios where they're really clean.
They're really clean, and they've bought their $2,000 Yazoo transmitter, and that's all they have.
Automatic antenna tuner. They don't even have to turn any knobs anymore.
Right.
And it's hooked up to their computer, so they use a mouse to tune their radio, which I don't even, what's the point if you're not going to turn any knobs?
And then there's the next step
and they're sending Morse with their mouse. They don't
even send it. They just type it.
Right, they type it. And
then the computer picks it up and translates it for them. You know, there's no telegraph key anymore. Yeah, I don't get it. That's not me.
Then there's the worst type of ham operator where they get their technician license and then don't do anything with it. That would be me.
Who are these people?
Someone we shall not mention.
Well, I haven't been too active either. My thing is, it's always been like this for me in ham radio. I like to build the radios and try them out to prove to myself they work, and then I almost never use them again.
Yep. Actually communicating with people? What's the point of that? You know,
I use it for a week, and I'm like, that was a big achievement. We got this thing to work. We got the design works. Everything's fine. Okay, move on to the next project.
Sweet. Oh, boy. Our amp hour's up. It is, sadly.
I have one last thing. I want to answer a question.
Go for it.
Okay. Someone wanted to know about, someone said that I saw Greg's website and some pics of his mother's senior design project, 4-bit ADC.
Yes.
Yes. My mother is an electrical engineer, and she's the one that got me into electrical engineering.
Wow.
That's
awesome.
Go.
Yeah.
So where did she go to school, and where did she work? Where did she work?
She went to school at Lawrence Tech, which is an engineering school outside of Detroit. It's very hands-on, and it's a co-op school. Mm-hmm. And she's now working at Ford Motor Company, still there. She worked at Ford and GM, bounced back and forth a few times, and she's at Ford right now to this day. She's now in purchasing. She's got an MBA and she's doing supplier quality. So, yeah, I know. Yeah.
You can just hear the collective groan of the 5,000 amp hour listeners.
Yeah, but then she knows all the tricks of the engineers. That's even worse. A purchasing agent that used to be an engineer is a very dangerous person.
It is, and it keeps them going over. She does a great job over there and keeps them going. Made it through all the cuts and everything. So that's sort of who got me into it. It's my mother.
So do you guys? And you said she got you into ham as well?
Yeah. Well, what happened was
she's a operator as well.
She's a ham as well. I remember I was into CB radio when I was 10. I started getting into CB radios, and I got all my buddies. Every kid on the block had a CB after I was done with them, and we would talk to each other. This was in 1990 when there's no cell phones or anything. We'd talk to each other.
Still, the CB craze was 70s.
Oh, it was. No one was on the CB except us.
Right.
10-year-olds.
That's great. Yeah, if you're not near a highway, you have the band to yourself, right?
Oh, man, it was great. We'd talk to each other, secretly at night, and we'd have like five of us 10-year-olds on there. It was so much fun.
That's awesome.
Yeah. And everyone had a CB in their basement from the 70s, so it's easy to get at people in the air. And I knew how to tune up the antennas and get the mothballs out of them. But anyway, my mom said, I was doing ham radio or CB radio for a few years. So I was like, right around age 13, she goes, I was buying another CB radio. And she goes, I don't want you to waste money on another CB radio. You're not learning, from that as much as you could from amateur radio. I don't want you wasting money on another CB radio. Let's get into amateur radio.
And my friends can't talk to me.
Yeah, they can't talk to, but I got all my buddies in the ham radio too, so I brought them along.
Oh, that's good.
Yeah.
That's awesome.
But her thing was it was expensive. It was getting expensive, that CB radio hobby. Let's do ham radio.
Build your own, right?
I'm so jealous.
Awesome.
Growing up, I didn't know a single person in my entire universe that was into electronics.
Oh,
until
really?
I was like 15, 16 and started to study this stuff. I knew absolutely no one. That's it.
Oh, it starts early. You got to start early. It helps.
Do you do any outreach stuff at MIT for doing the same kind of thing? Because
So
What kind of stuff?
I'm not. I'm sort of peripherally involved because I'm down in Connecticut now, focusing on the startup. So whenever they want help, I go up there, and help them. But there's a high school outreach that was a program that was done this past summer, where the high school kids built the coffee can radar.
Sweet.
Oh, wow.
Yeah, and it was great. It was like a huge success, and they had a blast because they actually got to do something cool. I mean, that radar is a lot of fun. It really works. Like, you can measure cars and people running down the street and all kinds of cool stuff. So it's a lot of fun.
Yeah, that's awesome. That could be another reason to, kid it up more, right? So,
Oh, yeah.
like we
Yes.
said, if any listeners are out there,
Yeah.
get kidding.
Yes, seriously. And let me know so I can tell other people.
That's
I get
great.
emails about 2-3 times a week asking for a kit of that, and I
Yep.
can't help them. It doesn't exist. So
Yeah, wow.
All right. Well, thank you very much, Greg, for joining us. It's been a
thanks for
blast.
having me, guys. Yeah, thank you for having me. It was a lot of fun.
And
Yeah.
where can we catch you?
Oh, you know what? Go to my blog, Mr. Vacuum Tube. That's where you find
Mr.
me.
Vacuum Tube.
Mr. Vacuum Tube.
And on Twitter as well, right?
That's right. Mr. Vacuum Tube is also on Twitter, and you'll see every fun engineering YouTube video I like. It goes up on Twitter for some reason.
Awesome.
Oh, yeah.
I'm subscribed.
But Mr.
great.
Vacuum Tube, the good stuff's on there. You'll see I put a lot of stuff up on Mr. Vacuum Tube. Yeah. Well, thanks for having me, guys. I love talking shop. I could go on for hours and hours.
I think we need to have a roundup of all the RF people we've had on at some point, and just have it out, and need to be able to sit back and listen.
Right.
Yeah.
Okay.
Yeah.
Free for
Yeah,
all.
they can.
We'd
Yeah,
have-
yeah. Talk about our trips to the Dayton Hamvention and stuff, and the guy with the antenna on his head.
No, you go to that a lot?
Oh yeah, my entire lab
go to-
is equipped
Yeah?
from the Hamvention. Everything.
Nice. Yeah, it
All
was
the-
during Maker Faire this year. I hope to make it next year, but it was during Maker Faire the same weekend this year.
I would go to Dayton over
So-
Maker Faire if you're trying to staff up a lab, or in terms of equip
Okay.
a lab rather. I would go there.
Right.
Man, you can
Yep.
get anything at Dayton. Anything. It's true. I mean, I
Sweet.
once saw a missile at Dayton. Yeah.
That's like Dave found a missile at that
at
shop.
that
right there.
junk store, yeah.
Really?
Yeah.
How much was it?
Yeah.
Oh, it wasn't actually a missile. It was just a nose cone,
Oh, okay. This was a missile. It was a Sparrow air-to-air missile at
Oh,
Dayton Hamvention.
wow.
Yeah. Yes.
Is that guy wearing a tinfoil hat?
I don't know. I couldn't imagine
I got
taking
this
that
in
home.
case they come for me.
My only question was, how do you take that freaking thing home? Do you strap it to the top of your car and drive down the freeway with it?
Oh, boy.
God, I'd love to see that.
TSA rubber glove time, folks.
Oh, man, yeah. It would be really bad then. Jeez, they'd have a good excuse to talk
You'll
to
be
you
making the 6 o'clock news.
Yep. All right. Well, thanks again, Greg. We really
Thanks, mate.
appreciate it.
then. Thanks for having me, guys.
See you, mate.
All right.
See ya.